All right, today we're tackling one of the biggest ideas in the universe, gravity. It's this invisible force that's, well, everywhere. It's what keeps your feet planted on the ground, what holds the planets in their orbits, and what literally shapes the entire cosmos. So, yeah, it's kind of a big deal. Let's dive in. You know the story, right? It all supposedly started with Isaac Newton and a falling apple. He sees this totally normal thing, an apple dropping from a tree. But then he looks up at the moon and asks this incredible question. Are they connected? Is the same force pulling on the apple also pulling on the moon? And it turns out the answer was a huge yes. And that one simple connection didn't just explain why apples fall down, it blew the doors off our understanding of the universe, revealing a single law that controls everything from a tiny pebble to a massive galaxy. Okay, so let's start right where Newton did, with that apple. How in the world do you connect a piece of fruit hitting the ground to the moon sailing smoothly across the night sky? Here's the genius part, and it's a little tricky to wrap your head around at first. Newton figured out that the moon is falling. It's constantly falling towards the Earth, just like the apple. So why doesn't it crash? Because it's also moving sideways at an incredible speed. It's moving so fast that as it falls, the Earth curves away beneath it. It's basically in a state of perpetually falling and missing. That's what an orbit is. Let me give you an analogy. Imagine you're whirling a stone on a string around your head. That string is constantly pulling the stone inward, right? That pull is called centripetal force. It means center seeking. Now, what happens if the string snaps? The stone doesn't keep going in a circle, it flies off in a straight line. Well, for the moon, Earth's gravity is that invisible string. It's the constant pull that keeps the moon from just flying off into deep space. And Newton's next big leap was realizing this wasn't just some special connection between the Earth and the moon. Oh no, this force was everywhere. This wasn't some local rule for our cosmic neighborhood. It was a law for the entire universe. And this is the heart of his universal law of gravitation. It says that every single object that has mass pulls on every other object with mass. It's true. You, right now, are gravitationally pulling on the device you're watching this on. And it's pulling back on you. Now, the force is so incredibly tiny you could never feel it, but it is there. And here it is, the beautiful math that describes it all. The force of gravity, F, depends on the masses of the two objects. The more stuff, the stronger the pull. But here's the really important part. That D on the bottom for distance. The force gets weaker with the square of the distance. That means if you double the distance between two objects, the gravitational pull doesn't just get cut in half. It drops to a quarter of what it was. It falls off a cliff, really. Okay, so we've been out in the cosmos. Let's bring this whole idea right back home and see how it affects every single one of us through things we talk about all the time, like mass, weight, and free fall. So what do scientists mean by free fall? It's actually pretty simple. It's just when an object is falling and the only major force acting on it is gravity. So for our purposes, we're kind of ignoring things like air resistance getting in the way. And when something is in free fall, it's not just moving, it's accelerating. It's getting faster and faster. And right here near the surface of the Earth, that acceleration is a constant number. We call it g, and it's about 9.8 meters per second every second. And the most amazing thing, something Galileo figured out centuries ago, is that g is the same for everything, no matter how heavy it is. If you could get rid of all the air, a feather and a bowling ball would hit the ground at the exact same time. This brings us to something people get mixed up all the time, mass versus weight. They are not the same thing. Your mass is the amount of stuff you are made of, your atoms, your molecules. That number never changes, no matter where you are in the universe. Your weight, however, is just a measurement of how hard gravity is pulling on your mass. So if gravity changes, your weight changes. And here's the perfect example. The moon is a lot smaller and has a lot less mass than Earth, so its gravity is way weaker. If you were to stand on the moon, your mass, the amount of you, would be exactly the same, but your weight, it would drop to about 1/6 of what it is here. That's why the astronauts could bounce around so easily. Now, gravity isn't the only player in the game. That constant downward pull is always interacting with other forces, and that's what gives us all sorts of everyday phenomena, like pressure and why some things float. Here's a little puzzle for you. Think about being at the beach. When you stand on the sand, your feet sink in. But if you lie down on the exact same sand, you don't. Why? In both cases, the force pushing down is exactly the same. It's just your body weight. So what's different? It all comes down to pressure. When you lie down, you're spreading your weight out over a really big area, the whole surface of your back. You have the same force over a large area, and that creates very low pressure, not enough to sink into the sand. But when you stand up, your entire body weight is now concentrated onto the tiny area of the soles of your feet. Same force, tiny area, that equals super high pressure. And that's what pushes the sand out of the way and makes you sink. It's the same reason a sharp knife cuts so well. It concentrates all your force onto a tiny edge. Okay, here's another classic. How is it possible that a gigantic ship made of thousands of tons of steel can float on water, but a tiny little steel nail sinks to the bottom instantly? I mean, they're both made of steel, which is way denser than water. What's going on? The answer is something called the buoyant force. Anytime you put an object in a fluid, like water, the water pushes back up on it. You felt this. When you get in a swimming pool, you feel lighter, right? That feeling is the buoyant force pushing you up. So, it's really a battle. You've got gravity pulling the object down, that's its weight, and you've got buoyancy pushing it up. A solid steel nail is super dense. Its weight easily wins the battle against the small buoyant force, so it sinks. But a ship is shaped to be mostly hollow air. Its average density, when you include all that air, is actually less than the water's. It displaces a massive amount of water, which creates a huge buoyant force, enough to hold up all that steel. So when you take a step back and you look at this whole story, you realize that Newton's law of gravity is so much more than a formula. It's this incredible, unifying idea that paints a grand design for the universe. I mean, just think about this. Before Newton, these four things were seen as completely separate, unrelated mysteries. The force that holds us on the ground, the path of the moon, the orbits of the planets, and even the rise and fall of the ocean's tides. Nobody thought they were connected. And then, boom, one single elegant law explained all of them. That's the power of a truly great scientific idea. Gravity is truly the invisible architect of our reality, from something as small as a single raindrop to the way entire galaxies are clustered together. It's a force we feel every single second of our lives, and yet there are still deep mysteries about its true nature we're trying to solve. It really makes you wonder, doesn't it? What other fundamental rules of our universe are hiding right there in plain sight, just waiting for someone to ask the right question?